Hey everybody, it's Mr. Oliver. Today I'm going to go over the solutions for the AP Physics 1 Unit 3 practice problems. This first video will be for the first question. So let's go ahead and get started. Alright, so for this first question, this is an old AP Physics B question. And the scenario is we've got a block of mass M sitting on this tabletop, and it says that the tabletop is frictionless, so we don't have to worry about any kind of friction going on up here. And what we're going to do is we're going to start off the block at the edge of the table and then compress the spring backwards a distance x. All right, and so what's going to happen is that block is going to gain some energy from the fact that the spring now has some elastic potential energy stored up in it. And then they're going to release the block, and it's going to fly off this tabletop and hit the ground through some kind of a projectile motion. And this is going to be a horizontally launched projectile. So what we want to do is we want to calculate some of these values. And normally you probably wouldn't do a big calculation, but these are all algebraic expressions. So on an AP exam of this type where we're having to do it at home, I would say that some kind of question like this would probably be likely where you do have to do algebra. So let's look at it real quick. It says the first question, or the first thing we do want to pay attention to, is that we have to determine our expressions in terms of these variables: capital M, capital X, capital D, lowercase h, and lowercase g. So we do have to include those, and those are the only variables that we can put in our answers. You can put numbers, but you can't include anything else. So for instance, it says it does not include the spring constant. So I can't put the letter K in here for the spring constant because it's not given to us. So what I need to do is put all my answers in terms of everything else, all these other variables right here. So the first question, we want to find the time elapsed from the instant the block leaves the table to the instant the block leaves the floor. And so if we look at this, whenever this projectile is launched in this parabolic path, if you remember for projectiles that the time to fall down some distance h is completely independent of the horizontal distance d. So all I need to do is treat this problem as though that block were just falling straight down from a height of h and determine the time of a free fall kind of problem. So to do that, I'm just going to look at a simple kind of setup where I have some block falling a distance of h. All right. Now, because gravity acts straight down and it's a constant value, you can use a kinematic equation. And so we can use y is equal to y naught plus v naught t plus 1/2 at squared. That's a kinematic equation. We'll assume that our final height is going to be down here at the bottom, so this variable right here will be 0. My initial position is up here at the top, so my initial position will be h. My initial velocity, well, I'm just dropping this block from rest. Now, granted, it is moving horizontally in real life, but in a vertical direction, it is not moving at all. So we'll assume that this initial velocity term is 0. So 0 times time is 0. And then for the acceleration, of course, that will be acceleration due to gravity g. And so now at this point, all I need to do is calculate the time. Now, we've kind of done something kind of weird here. We're assuming that this final height is 0, or this final position is 0, and its initial position is h. And you're going to get some kind of weird structure of this algebra where you have a negative sign. But that's okay, because if you remember, g is also technically negative. So these negative signs can cancel out. And so we have h is equal to 1/2 gt squared. And all we need to do is solve this for time. So I'll multiply by 2, divide by g, and then take the square root to get time by itself. So for part A, your expression for the time is square root of 2 times the height over g. And that's your solution for A. Now question B says we want to determine the horizontal component of the velocity of the block just before it hits the floor. Well, that's actually pretty easy, because if you remember, for projectiles, horizontal velocity, as this thing falls down, the horizontal velocity is constant. So whatever it launched off at with V naught, that's going to be the same as the horizontal velocity right before it hits the floor. It's going to be the same as the horizontal velocity at any point between where it launched and where it hit the floor. So that horizontal velocity value is constant. And so that's what we want to find, is we want to find the horizontal component of that velocity. Well, how do I do that? Well, for constant velocity kind of problems, if you have a constant velocity, that is just simply equal to the distance that something is traveling divided by the time that it is traveling that distance. So for question B, all I need to do is put my expression for distance, which they give us in the problem. It says it travels a distance of d, so that's a capital D. And then the time is the time that it took to travel that distance d. Well, that's going to be the same time as which it took to get down to the ground. And we got that in the previous problem. That was just the square root of 2 times h over g. And so that's going to be your answer for question B. That's going to be the horizontal component of its velocity. Now, some people will say, well, don't I have to rationalize this, get rid of that square root in the denominator? No, you don't have to. You can just leave it as is. Physicists don't care about rationalizing equations unless it just helps them mathematically, but we don't have to do that. All right, question C. Question C says we want to calculate the work done by the spring. Work done on the block by the spring. Okay, so the big key point, this is one of the biggest points in the energy unit, is that work we can calculate many different ways. You can calculate it as force times displacement, and it's actually a dot product between two vectors. You could also calculate it by f d cosine theta. That's kind of the expression for the dot product. Well, the problem is I don't know anything about the force, the spring force, because that's the force that's pushing that block. So I can't use this expression at all. I can't use either one of these. But if you remember, the big idea about work is that work changes energy. That's what you want to remember in most of these work style questions. What is the work? What is the work? Well, the work is equal to the change of energy. Well, what kind of energy did we have in this problem? Well, during the time that the spring is pushing the block, it starts from rest and then it speeds up. So that means that spring right here is adding kinetic energy to the block. So the kind of energy that's changing is kinetic energy. And so that's the specific type of energy change that we got. And so if you remember, a final is just a change in energy is always the final energy minus the initial energy. Well, because the block started at rest, there is no initial kinetic energy. So therefore, the work done on the block is going to be equivalent to the final kinetic energy. Well, kinetic energy is just 1/2 mv squared, where this v is the final speed. And that final speed has to be the speed that it launched off the end of the table. So that's this velocity going horizontally. Well, that's just what we got up here. That's the same velocity as what we calculated in B. So this is V final. That whenever you push this block with the spring, it adds some velocity to it, which is the same velocity that it launched at horizontally. So we already have our expression for the V final. So therefore, do a little bit more substitution. 1/2 the mass times V final squared, which is going to be this big expression d divided by the square root of 2h over g. And that entire thing is squared. And if you wanted to, you could leave it there, but let's just go ahead and kind of simplify this a little bit more. So we'll have 1/2 the mass times d squared. I'm just going to kind of do this all up here. D squared divided by, well, we got a square root, so when you square a square root, the square root goes away, divided by 2h over g. Well, I don't want to put a fraction down here, so I'm going to put the g back up top. So it's 2h divided by g. The g comes up here. And so if you have a 1/2 and a 2 both in the denominator, or a 2 here for the 1/2 and this 2, that becomes 1/4. So you end up with an equation that says it's 1/4, 1/4 times mg d squared divided by 2h. All right. Actually, this should be a capital M, sorry. And so that's the amount of work that the spring does to the block. All right. And then lastly, we want to calculate the spring constant. So the spring constant we can get from that work term. Okay. Earlier we said that the work is equivalent to a change in energy. Okay. So yes, the work done by the spring on the block gave the block some kinetic energy, but it also means that the work from the spring has to have had that same amount of energy. So I can actually change this energy type to a change in the elastic potential energy, US. Okay. Well, if you don't recall, the equation for elastic potential energy is 1/2 kx squared. Right. So what I can do is do 1/2 k final squared minus 1/2 k initial squared, or kx initial squared, where the initial distance here is what we're talking about. Okay, so now once again, you're going to get some kind of a negative term, because finally, after that spring has been relaxed and pushed the block to the left, this distance x will be in 0. And so we'll have a negative 1/2 k x initial squared. Well, if you think about it, if you gained kinetic energy and lost elastic potential energy, then that means that the change in energy did decrease. So it's okay, you know, you can kind of ignore this thing. Just know that any loss of the potential energy in this negative term resulted in a gain of kinetic energy from before. So you can still set this equal to 1/4 mg d squared over h. And guys, I apologize. Previously, there should be no 2 there. There's only an h. Because I'd multiply the 2 and the 2. That becomes 4. All right. And so we can set this equal to 1/2 k x initial squared. And so now it's just a matter of algebra and solving for the k. So if I have 1/2 over here, I can get rid of this, and this will become 1/2 on the left. So I have 1/2 on the left. I need to divide by k, or I'm sorry, x squared, x squared. And so then we get k by itself. So k is equal to mg d squared divided by 2h x squared. And that's your expression for k. All right. And this was an old, like I said, an old free response question from AP Physics B, but the point breakout wouldn't be the same as what you would do. I'll just let you know what the points were. For A, this was worth +3. For B, that was worth +4. Actually, that's an easy one. +4. For part C, this was worth +4. And for D, this is worth +4. But like I said, if this was an AP Physics 1 test, the point breakout would not be the same. All right, and that's the solution for question 1. If you have any questions, guys, just shoot me an email, and I'll be glad to help you out. Thanks a lot. I'll see you on the next one.